Hello everyone. Our today's lecture is linear independence of vectors, basis and dimension. I assume that you all are familiar with the basic concepts that are needed in this lecture. Basic concepts are homogeneous system of linear equations that are given in lecture 4, vector spaces lecture 5 and linear span lecture 6. So let us start with some basic introduction. So before talking about vectors, let us start with the real numbers, variables x and y, call them scalars. Suppose you have an equation written as y equals to 2x, where y and x are scalars belonging to set of real numbers. It can be clearly seen here that y depends upon x. Y equals to 2x means y can be written in form of x. So I can write this equation as minus 2x plus y equals to 0. This equation is a linear combination of two variables x and y. Further, if I take a1 equals to minus 2 and a2 equals to 1, that means I can write this equation as a1x plus a2y equals to 0. So here I can say that y and x are dependent whenever their coefficients a1 and a2 are not equals to 0. I will use this concept to define linear independence or linear dependence in vectors. Our first definition is linear dependent vectors. If V be a vector space over a field F, as I had already told that in our lectures we will consider field F either real numbers or complex numbers. So here V be a vector space over a field F and u1, u2, um are m vectors belonging to vector space V. We could say that these vectors are linear dependent if and only if there exist some scalars a1, a2, so on, am in field F, not all 0, such that a1 into u1 plus a2 u2 plus a3 u3 so on am equals to 0. So a set of vectors say u1, u2, um are linearly dependent whenever you take the linear combination of these vectors, and if the coefficients, the scalars a1, a2, a3 are not all 0, then u1, u2, um are said to be linearly dependent. Here not all 0 means that you have a1 equals to 0 say and a2 is not equals to 0. Moreover, say a3 equals to 0, a4 equals to 0, so on am equals to 0. Then in that case also you will say that u1, u2, u3, um are linearly dependent. What is linearly independent? If in this combination all scalars, all the coefficients a1, a2, am come out to be 0, then I will say that the vector u1, u2, um are linearly independent. Let us explain this definition with the help of example. Suppose you have a vector u1 equals to 110, u2 132, u3 495. These u1, u2, u3 vectors belongs to vector space R3. Now we want to check here that whether these vectors are linearly independent or dependent. In that case, we will move according to the definition. I will write here the linear combination of these vectors alpha u1, beta u2 plus gamma u3, where alpha and beta gamma are the scalars from field F, and I will put this linear combination equals to 0. Now these vectors u1, u2, u3 will be linearly independent if alpha, beta and gamma all will be 0. So how can we find that alpha, beta, gamma be 0? I will put the value of u1, u2, u3 in this equation. So this equation will become like this. So multiplying first vector with alpha, second vector with beta, third vector with gamma, we have alpha plus beta plus 4 gamma equals to 0. alpha plus 3 beta plus 9 gamma equals to 0, and 0 alpha 2 beta plus 5 gamma equals to 0. Here you can say that we have a homogeneous system of linear equation with three unknowns. The unknowns are alpha, beta and gamma. So from this set of system of linear equation, I have to find out the value of alpha, beta, gamma. So since it is a homogeneous equation, either it will have zero solution or non-zero solution. If it has zero solution, that means alpha equals to beta equals to gamma equals to 0, then I can say that u1, u2, u3 is linearly independent. Independence or dependence of these three vectors depend upon the value of scalars alpha, beta, gamma in the homogeneous system of linear equations. So let us solve this homogeneous system of linear equation. I reduce this system of linear equation to echelon form. After reducing to echelon form, I have two equations. I have two leading unknowns. In this equation, number of equations are less than number of unknowns, so this system has non-zero solution. So that means value of alpha, beta, gamma come out to be non-zero. So if it has non-zero solution, then I can say that this system is linearly dependent. So these three vectors u1, u2, u3 are linearly dependent vectors. Consider another example, second example. Now in this example I have taken three vectors u1, u2, u3. Again, to check that these vectors are linear dependent or independent, I have considered the linear combination of these vectors where alpha, beta, gamma are scalars. So the equation will be alpha plus 2 beta plus gamma equals to 0, 2 alpha plus 5 beta plus 3 gamma equals to 0, 3 alpha plus 7 beta plus 5 gamma equals to 0. Reducing this equation to echelon form by applying row operations, we have alpha plus 2 beta plus gamma equals to 0 and 2 gamma equals to 0. Number of equations equals to number of unknowns. In this homogeneous system of linear equation, we will have zero solution, that is alpha equals to beta equals to gamma equals to 0. Scalars alpha, beta, gamma are 0. I can say here that u1, u2, u3 are linearly independent. Let us explain this concept with the help of one more example. Let V be a vector space over a field F and u1, u2, u3, um are vectors in V. I suppose here that one of the vector is the zero vector in this set of vectors. For simplicity, let us assume that u1 equals to 0, and I want to check that whether these vectors are linearly independent or not. So in order to check that whether these are linearly independent or not, I have to write the linear combination of these vectors and put it equals to 0. So let us a1, a2, am be the scalars from field F such that a1 into 0 vector, as I have assumed that u1 is the 0 vector, plus a2 into u2, a3 into u3, so on equals to 0. Now u1 is the 0 vector, so I can choose that a1 is not equals to 0. For other vectors u2, u3, um that are non-zero vectors, I will take a2 equals to 0, a3 equals to 0 and am equals to 0. Here not all the coefficients a1, a2, a3, am are 0. At least one coefficient a1 is non-zero. Others are 0, but not all are 0. So I can say here that this set of vectors u1, u2, um will be linearly dependent. So if the set of vectors contains 0 vectors, then that set of vectors will be linearly dependent. Suppose you have only a 0 vector, so that 0 vector is linearly dependent. It is easy to prove that if you have a coefficient or scalar alpha, then alpha into 0 equals to 0 vector. So here alpha will be non-zero. So in that case I can say that 0 vector is linearly dependent. As we have already explained linear span in previous lecture, and in this lecture we have explained that what are linearly independent set of vectors, we are in the position to define basis. Let V be a vector space over a field F, where F is either a real number or a complex number in our lectures. Let U1, U2, Um be vectors belonging to V. Let S be the set of vectors containing U1, U2, Um. So this set S U1, U2, Um is called basis of V. Number 1. If U1, U2, Um are linearly independent, or I can say that set S is linearly independent. Number 2. If U1, U2, Um spans V, that means every vector of V, say we have a vector small v belonging to vector space V, if and only if every vector of V can be written as linear combination of U1, U2, Um. So this is the definition of linear span. For more clarification, you could watch my previous lecture on linear combination of vectors. So, if u1, u2, um are linearly independent and every vector v of vector space V can be written as linear combination of u1, u2, um, then I will call set S a basis of V. Now number of elements in this basis are m, or I can say that cardinality of this set S is equals to m. So I here define dimension of vector space V. The dimension of vector space V is equals to m. Dimension of vector space V depends upon the number of vectors in the basis of vector space V. For a set of vectors to be a basis of vector space V, it should be linearly independent and it must span vector space V. Let us watch some examples of basis. So consider a vector space R4. Let B1 be the set of vectors from R4 containing vectors 1 0 0 0 1 0 0 0 0 1 0 0 0 0 1. So this set B1 is the usual basis of vector space R4. We call this set a usual basis. It is a basis because this set is linearly independent. You can easily see here that if we take linear combination of these vectors alpha plus beta of E2 plus gamma of E3 and delta of E4 and put this linear combination equals to 0, where alpha, beta, gamma, delta are scalars belonging to field F, what we will have here, alpha, beta, gamma, delta equals to 0 vector, 0 0 0. So value of alpha equals to 0, beta equals to 0, gamma equals to 0 and delta is also 0. So it satisfies condition 1, that is this set is linearly independent. Condition number 2, this vector should span vector space R4. So in that case any vector x, y, z t in R4 can be written as linear combination of these vectors. You can easily see here that every x, y, z, t of R4 can be written as linear combination of these vectors, x of 1 0 0 plus y of 0 1 0 0 plus z of 0 0 1 0 plus gamma of 0 0 0. It also satisfies the second condition that B1 spans R4. So we can say here that B1 is the basis of vector space R4. Another basis of R4. It is also the basis of R4. I can prove that this B2 set is linearly independent, and also this B2 set spans R4. This B2 set is also the basis of vector space R4. You can find infinite number of bases of vector space R4, but all the bases contains only 4 vectors, and the dimension of vector space R4 here is 4. Another basis B3 is, so let us move to another example. Vector space P4T of all polynomials of degree less than equal to 4. That means here the vector space P4T contains elements of type A0 plus A1T plus A2T square plus A3T cube plus A4T4, where A0, A1, A2, A3 are scalars belonging to field F. So what will be the basis of this vector space P4T? And the basis of this vector space is 1 T, T square, T cube, T4. It is linearly independent. How? Take a linear combination. So here linear combination will be A0 plus A1T plus A2T square A3T cube plus A4T4. Put it equals to 0. Compare the coefficient of T, T square, T cube and T4. You can see here that A0, A1, A2 so on all are 0. So this set is linearly independent. Moreover, every vector of P4T can be written as linear combination of these 5 vectors. So here P4T is a vector space, B1 is the basis of the vector space P4T, and dimension of P4T equals to 5 because basis contains 5 elements. Another basis of P4T is B2, 1 1 plus T, 1 plus T plus T square, T cube, T4. So this set is also linearly independent, and every element of P4T can be written as linear combination of basis 2. Move to another example. Vector space all 2 cross 2 matrices. So here the basis will be 2 cross 2 matrix 1 0 0 0 1 0 0 0 0 1 0 0 0 0 1. So this set is linearly independent, and this set also spans M2 cross 2. You can see that every element of M2 cross 2 can be written as like. Let us try to understand this concept of basis and dimension more clearly. Let V be a vector space of finite dimension M. What finite dimension M here means that there exist vectors u1, u2, um belonging to vector space V such that B is the basis. If the elements in the basis are finite, if cardinality of B is finite, then we will say that vector space is finite dimensional. If the elements on the basis are infinite, in that case we will say infinite dimension vector space. So here I am considering that V be a vector space of finite dimension M. Any m plus 1 or more vectors are linearly dependent. What does here mean? So first we have considered that V be a vector space of finite dimension M. That means there will be some basis B in V containing m elements u1, u2, so on um. So here I am saying that if a set contains more than m elements, suppose for easiness I construct a set as containing more than m elements. For here I have taken first m elements from the basis and another m plus 1th element. So now this set S contains m plus 1 vectors, and I want to show that this set S is linearly dependent. It is very easy to explain. As you know that B is the basis, B is linearly independent and B spans V. So every vector of V can be written as linear combination of elements of B. So that means this plus 1, which is also belongs to V, can be written as linear combination of vectors u1, u2, so on, So I rewrite this equation as a1 u1 plus a2 u2 plus so on am plus minus 1 of plus 1 equals to 0. So here I have linear combination of vectors u1, u2, u3, so on and plus 1. But one of the coefficient is non-zero. Which one? This one. This coefficient is equals to minus 1, or I can say here that coefficient am plus 1 is not equal to 0. Then by the definition of linearly dependent vectors, we can see here that if I write linear combination of these m plus 1 vectors, then not all the coefficients are 0. Okay? At least one is non-zero. So any m plus 1 or more vectors are linearly dependent whenever the dimension of vector space V is m. Second, any linearly independent set S with m elements is a basis of V. To S be a basis of V, I have to prove two parts. Number one, that is S must be linearly independent, which is already given. Second, I have to show that S spans vector space V, which is also very easy to prove. Let us assume that S is not a basis of U. Then there is some basis of U, that will be B, V1. As the dimension of V is m, then basis B contains m elements. Since u1, u2, are also elements of vector space V and are linearly independent, I can write vector u1 as linearly combination of vectors v1, v2, vm, where alpha 1, alpha 2 are scalars belonging to field F. Similarly, I can write u2 as linear combination of vector v1, v2, v3, vn, so on, um. So in that case, I can consider that if W be any element of vector space V, then this W can be written as linear combination of vectors u1, u2, because u1, u2, can further written as linear combination of v1, v2, vm. It is the transitivity property. Suppose W is equals to u1 plus u2, then u1 can be written as alpha 1 v1, alpha 2 v2, so on, and also u2 can be written as beta 1 v1, beta 2 v2, so on. So I can say here that W can be written as alpha 1 plus beta 1 v1 plus alpha 2 plus beta 2 v2. Every vector of V can be written as linear combination of u1 and u2. That means the set S, which contains m linearly independent vector, is also a basis of V. So I think these concepts will make it clear that what are the linearly independent vectors and what are linearly dependent vectors and how basis is defined. A linearly independent set of vectors that spans vector space V is called basis, and number of elements in the basis are called dimension of that vector space V. So by this I conclude my lecture. Thanks for watching, and please like and subscribe for more videos.